Percent composition is used to define the ratio of different components that are within a impure substance or a blend of something, a mixture. What percentage or what fraction of this mixture is composed of this particular pure compound? Molecules and compounds are mixtures of these different chemical elements that are all bound together in different ways through the chemistry. And by identifying the percent composition of individual components within a molecule, you can define a lot of characteristics about that particular molecule or compound. Compounds and molecules are made up of individual atoms, and knowing the percent composition of these molecules and compounds can indicate what the ratios are within a reaction as it goes from reactants to products. So all chemical reactions start with the reactants and they end with the products. They're going in that direction. But how much of one versus the other requires a lot of measurements to determine how much product you actually have, how much reactant did you start with, and those sorts of measurements. In a previous experiment that was where you were looking at solubility, that was a qualitative experiment where you were performing a number of different reactions and seeing all of the different results. You could identify the different compounds that were created, but that was it. This experiment looks at how much of the compound is created or how much is present. And this would be referred to as a quantitative experiment where you're measuring an exact and precise amount. In previous experiments, the measurements that were taken or the mass measurements that were taken were done on beam balances, which would read to 2 or 3 decimal places. The measurements for this experiment are done on digital balances, which can read 4 decimal places. There are more advanced and expensive digital balances that can read either 5 or even 6 decimal places. But in this case, you're going to be recording the values out to 4 decimal places. So, as I said, molecules are made up of all of the different elements held together through chemical bonds. Or in the case of ionic compounds and salts, they're held together through electrostatic interactions, positive ions and negative ions coming together. And you can look at a molecule itself and see the ratio or the molecular ratio of the atoms. So in the case of water, water is H2O. There are 3 atoms total in one molecule of water. There are 2 hydrogen atoms and 1 oxygen atom. The ratio of hydrogen to the molecule is 2 to 1. Every 1 molecule of oxygen has 1 molecule of water has 2 atoms of hydrogen, and the ratio with oxygen is 1 to 1. For every 1 molecule of water, there is 1 atom of oxygen. However, oxygen and hydrogen weigh a different amount. Overall, the atomic or the molecular weight of water is 18 grams per mole. 16 of those are coming from oxygen, this 1 oxygen, and the other 2 are spread across 2 hydrogen atoms. So overall, while it based on just the number of atoms, there are more hydrogen atoms present in a molecule of water. The overall amount is that it is more heavily based on oxygen than the hydrogens. So looking at this and looking at these ratios between how many atoms there are in molecules and what percentage of that is what this experiment is focusing on. So it uses the chemistry concept of the mole. And a mole is a number. So just like you can have a couple, which is 2 of something, you could have a dozen or 12 of something, a baker's dozen of 13. You can have a mole of something, which is 6.02 times 10 to the 23rd. It's a very, very large number. And this is the unit that chemistry uses. So when you're performing chemical reactions, you're dealing in the unit of moles. And 1 mole is 6.02 times 10 to the 23rd atoms or molecules. And pretty much every single time, if you're given a mass is something that's done in a lab setting. This is what's in the physical world. You're measuring a mass of a compound or a chemical and weighing it on the balance. But the chemistry occurs in moles. Each atom weighs a different amount. So while the mass as a whole can be measured physically, the actual amount of those individual atoms is based on the moles. So when you're going through and you're given a mass of something in a question or in a lab, it's best to always convert it to the number of moles that it actually is. So if you're given a mass, that can be converted to moles by dividing by the molecular weight. So if you look at this, the molecular weight is in units of grams per mole. And if you're dividing by that, it's the reciprocal, moles per gram. In this way, grams cancels out, and you're left with the unit of moles. The same thing can be true the opposite way. If you need to determine what is the mass of something given the number of moles, this is done by multiplying the molecular weight by the number of moles. In this case, the molecular weight unit is grams per mole, and you're multiplying it by moles, so the unit of moles cancels out, and you're left with grams. Overall in chemistry, there's a lot of this interconversion between grams and then moles to grams. And this experiment focuses on these types of conversions. You're going to be going from grams to moles, from moles to moles using the chemistry, and then from moles back to grams of something else. Percent composition is many times looked at as percent by mass, or the sheer amount of a substance that's present. And in chemistry, when looking at a percent by mass, you have to look at the periodic table and see the individual molecular weight and atomic weight of the different components. Using the periodic table, you can define the molecular weight of a compound by adding up the individual atomic weights or atomic masses of all of the elements contained within that molecule. When you add all of these together, this is the amount of mass that is needed to contain 1 mole of the molecule. So You've probably gone over these already before, but when you're looking to determine the molecular weight of a compound, you're taking the individual atomic masses of the overall compound itself and adding them all together. So in this case of copper 2 sulfate, it's CuSO4. There is 1 copper, 1 sulfur, and 4 oxygens. So looking at the periodic table, you can find the atomic mass for each of these individual atoms, and then you're adding them all together to determine the molecular weight of the entire compound. So 1 copper atom has a mass of 63.55 grams per mole. This is directly from the periodic table. 1 sulfur atom has a molecular weight of, or atomic weight of 32.06 grams per mole. And oxygen has an atomic weight of 16.00 grams per mole, and there are 4 of them. So when you multiply these together, overall in the compound of copper sulfate, there's 63.55 grams per mole of copper, 32.06 grams per mole of sulfur, and 64.00 grams per mole of oxygen. When you add all of these together, this is the molecular weight of copper sulfate at 159.61 grams per mole. This is the mass that is needed in order to make up 1 mole of this compound, 1 mole of copper sulfate molecules. So 6.02 times 10 to the 23rd individual molecules of copper sulfate weighs 159.61 grams. Using the molecular weight is how you can determine the percent composition directly from the formula. So the example here is of sodium bicarbonate. Again, you go through and you figure out the molecular weight of the entire compound first, seeing the atomic weight of each of the individual atoms and multiplying that by how many atoms there actually are in the compound. When you're determining a percent composition, it can be just of a single element within the compound, or it could be a whole section. So the experiment today is looking at the percent carbonate. Carbonate is not an individual ion. Carbonate itself is made up of both carbon and oxygen and has a molecular weight that you can be determined to be 60.01 grams per mole. So in either case, you know the total mass of sodium bicarbonate. You know in this case, you can know the mass of 1 sodium atom or of 1 carbonate that is contained within the compound. When you divide the mass of the component by the mass of the entire compound multiplied by 100%, that will give you the percentage by mass of the component. So in this case of sodium bicarbonate, you have a total mass or a total molecular weight of 84.008 grams per mole. 22.99 grams of that comes directly from the sodium. So the percentage of that would be 27.37% sodium. That's how much sodium, or that's how much, that's the percentage of sodium bicarbonate that is made up of sodium. When you determine the molecular weight of carbonate itself at 60.01, you again can divide that by the molecular weight of the entire component to figure out that sodium bicarbonate is 74.43% carbonate. So going through, looking at these different compounds and looking at what types of atoms and components they're made up of, you can see how the reactants react and form the individual components and individual products, and look at the ratios between the two. This experiment looks at the percent composition of different carbonate compounds. In the first part of the experiment, you're particularly looking at the percent composition of baking soda and baking powder. Baking soda is a pure compound, sodium bicarbonate. Baking powder is a blend of a number of different compounds, one of which is baking soda. Baking soda and baking powder are both white powders that are used in baking. While baking soda is a pure compound of sodium bicarbonate, baking powder, however, is a blend of 4 different components. The 4 components that make up baking powder are baking soda or sodium bicarbonate, cornstarch, sodium aluminum sulfate, and calcium phosphate. All 4 of these components are white powders, and when blended together, they comprise baking powder. The first part of this experiment focuses on determining the percent composition of baking powder and figuring out what percentage of baking powder is comprised of baking soda. The experiment itself looks at the percent composition, in particular, the percent carbonate. All of the components and all of the compounds that you're looking at are different carbonate compounds, one of which is sodium bicarbonate or baking soda. Carbonate is an anion and cannot be directly measured just by weight or in labs like this. However, using chemistry, you can take something that is difficult to measure and react it to form something that is easier to measure, to form an easily measured product. Then, using the chemistry, you can back calculate to figure out how much of that initial reactant there was. In this experiment, we're reacting carbonate with hydrochloric acid. When a carbonate reacts with hydrochloric acid, it generates water and carbon dioxide gas. After the reaction is complete, the carbon dioxide was released as a gas, and therefore the total mass present is now less than what was started with. The difference between before and after the reaction is the mass of carbon dioxide. When you have a mass of something, you can figure out how many moles you have. Then using the chemistry, work back to look through the balanced chemical reaction and determine how many moles of starting material that came from. In this case, once you have the moles of carbon dioxide, you can figure out the moles of carbonate ion. And from the moles of carbonate ion, you can use the molecular weight and figure out how many grams of carbonate were present based on the total mass of sample. While percent composition can be determined through chemical formula and molecular weights, many times, especially in a lab setting, it needs to be done experimentally through actual measurements, whether that be mass or absorbance or other different types of measurements that are performed in the lab. This experiment focuses on the reaction of different carbonate samples with hydrochloric acid. So any type of carbonate compound will react with any sort of an acid to form water, carbon dioxide, and the salt of other ions. As you go through chemistry in this course and the lecture course, you'll look at how these different chemical reactions can be separated out and then condensed into specifically the type of reaction that's going on. In this case of sodium carbonate, one molecule of sodium carbonate will react with 2 molecules of hydrochloric acid to form 1 molecule of water, 1 molecule of carbon dioxide, and 2 molecules of sodium chloride salt. However, the phase of the individual components, it plays a role in what's actually going on. The aqueous phase indicates that this compound is dissolved in water. It is an ionic compound that dissolves and breaks apart into its individual ions. This happens with sodium carbonate, hydrochloric acid, and the sodium chloride product. Overall, looking at the ions themselves, you have 2 sodium ions, 1 carbonate ion, 2 H+ ions, and 2 chloride ions reacting to form 1 water molecule, 1 carbon dioxide molecule, 2 sodium ions, and 2 chloride ions. These sodium and chloride ions are the same on both the products and the reactant side, indicating that they did not play a role in the actual reaction. By canceling these out, you're left with the full actual reaction of what's going on. The carbonate component reacts with the H+ component to form carbon dioxide and water. Many times in chemical reactions, when you're trying to look at one component, that can't really be measured directly. You need to perform some sort of a reaction on it in order to directly measure one of the products and then work your way back through the chemistry to figure out what that initial thing is that you're trying to look at. That's the case in this reaction. Carbonate itself is an anion that you can't really measure directly. Ions themselves can't be isolated without the other counter ion present. You cannot have just carbonate ions, negatively charged anions, without a positively charged cation to balance it. So measuring the amount of carbonate only present in a sample directly is very, very difficult. And what is usually done is it undergoes a reaction, and through the reaction generates a product that you can measure. In this case, we're measuring the carbon dioxide and then using the chemistry of this reaction to figure out, based on the amount of carbon dioxide, how much carbonate was there to start. So the first thing you're looking at is how much total mass of sample do you have. In the experiment, we're measuring an empty beaker, an empty vial, and an amount of acid. This experiment has conservation of mass. Every amount is accounted for, even the mass of the liquid acid. So to start out, you're measuring an empty beaker, an empty vial, and a pipette filled with acid. Then some of the sample is placed in the vial and the mass is recorded again. The difference between before and after is the mass of the sample that was placed in the vial. After that, the reaction occurs. You're mixing the two components together. You're mixing the acid in the pipette with the carbonate sample in the vial. This causes the reaction to generate water and carbon dioxide. Carbon dioxide itself is a gas, and that bubbles away, meaning the overall mass is decreasing. So the mass after the reaction is finished is lower than it was at the beginning. The difference between these masses before and after the reaction is the mass of carbon dioxide that escaped and bubbled away. So now you have an actual mass of a direct product, the carbon dioxide gas. Based on the molecular weight of carbon dioxide, which is 44.01, you can determine how many moles of carbon dioxide were generated from the reaction. So if you have this amount, 0.3387 grams of carbon dioxide, dividing that by the molecular weight of carbon dioxide gives you 0.007696 moles of carbon dioxide gas. Once you have the moles of a compound, you can then look at the reaction itself and look at the ratios between the molecules in the balanced reaction to figure out the masses of any of the other components within that reaction itself, either products, other products, or reactants. So looking at the reaction itself, one carbon dioxide comes from one carbonate. The reaction ratio is 1 to 1. So if you have the moles of one component and the moles of another component, you can look at that ratio and cancel them out, or cancel out moles of CO2, and you would be left with moles of carbonate. In this example and throughout this experiment, the moles of carbon dioxide is equal to the moles of carbonate because it is a 1 to 1 reaction ratio. That means that this 0.007696 moles of carbon dioxide came from and was generated by 0.007696 moles of carbonate anion. So you've taken a mass, converted it to moles, and used the reaction ratio within the balanced chemical equation to determine the moles of the other component in the reaction. Now that you would have the moles of the other component, you're converting that back into grams. So you're taking that mass and multiplying it by the molecular weight of carbonate to determine the mass of carbonate. Once you have the mass of carbonate, you can then figure out what the percentage of this carbonate was of the whole sample itself. You have the mass of the individual component, and you have the total mass that was the first measurement. So initially, the total mass was 0.6616 grams. The mass of the component was 0.4619 grams. So by dividing them and multiplying by 100%, you can figure out that the sample itself in these measurements came out to be 69.81% carbonate. Overall, this experiment is focusing on measuring the percent composition of something, in particular the percent composition of different carbonate compounds. You're going through this, you're looking at the masses of before and after the reaction to figure out the mass of carbon dioxide, leading way to the mass of carbonate, and determining the percent carbonate of sodium bicarbonate, the percent sodium bicarbonate within baking soda, as well as the percent carbonate of an unknown compound, and comparing that to the list of possible carbonates to identify what is your unknown carbonate.